Theovis, the idea made visual.
Drop a bead of dye in still water. Sharp at first, then it softens, spreads, and fades into a smooth glow.
And it never sharpens back up on its own?
That one-way softening is the heat flow, the universe's smoothing machine. It blurs photos, rounds shapes, and cools your coffee, all with the same rule.
What's the rule behind the smoothing?
At every point, the temperature changes toward the average of its surroundings. Hot spots leak into cold ones.
So bumps sink and dips fill in.
Always. The rate of change equals a constant times the Laplacian, the curvature of the temperature. That's the heat equation.
In one line, the time change of temperature equals alpha times its Laplacian, where alpha is the diffusivity of the material.
And a single point of heat spreads out as a Gaussian, a bell curve.
A bell curve that gets wider and flatter as time runs. Its width hides a famous law. Start with all the heat at one spot. Instantly, it begins to spread into a smooth bell, lower and broader every moment.
How fast does it widen?
The width grows like the square root of time, not time itself. To spread twice as far, you must wait 4 times as long. That square root creep is the signature of all diffusion.
Put a number on that square root law. The spread, sigma, grows as root t.
To double the spread, you need 4 times as long. Diffusion is painfully slow over distance.
It's why a sugar cube takes ages to sweeten still tea, but stirring, which isn't diffusion, does it in seconds. You can watch the equation happen. A drop of ink in still water starts as a tight, dark point.
And it blooms outward into a soft cloud, fading at the edges.
Every blurry edge there is the heat equation in action. Sharpness leaking away into smoothness and never coming back.
Why does heat smooth instead of, say, scramble?
Break any shape into waves. Fourier's idea. Heat shrinks each wave, but a high-frequency wave shrinks far faster than a slow one.
So the fine, jagged detail evaporates first, leaving the broad shape behind.
Exactly. Each wave decays like e to the minus k squared t. The k squared is everything.
Here's a jagged signal built from many waves. As heat runs, watch the sharp wiggles melt, while the gentle curve survives.
It's a low-pass filter. It keeps the smooth and erases the sharp.
That's precisely why a Gaussian blur softens a photo. Blurring is just letting heat flow across the image for a moment. Compare 2 ripples, one twice as fine as the other. Their decay rates go as k squared.
Doubling the frequency quadruples the decay rate. The fine ripple dies 4 times faster.
Stack that effect across all the fine detail, and you see why heat leaves only the smooth, slow shape behind.
Could the smoothing ever accidentally create a new peak somewhere?
Never. This is the maximum principle. Heat flow can only lower the highest point and raise the lowest. It cannot invent a new extreme.
So everything marches toward flat and uniform.
Toward the average.
Smoothness isn't a side effect of heat, it's the whole destination. Apply the same idea to a shape's outline. Let each point move inward by its curvature. Sharp dents and spikes flow the fastest.
And the wobbly blob rounds itself into a circle.
That's curve-shortening flow. Heat for geometry. A loop always smooths into a perfect circle before it disappears. Make it concrete. Copper conducts heat well, with diffusivity about 10 to the minus 4. How long to warm a point 10 centimeters in?
Length squared over alpha, about 100 seconds.
And to reach twice as deep takes 4 times as long. The square root law again. Even a great conductor is slow over distance. Here's the catch worth stating plainly. Heat flow is irreversible. Run it backward and the maths blows up. Tiny errors explode.
So, enhancing a blurry photo can never truly recover what diffusion threw away.
Smoothing destroys information for good. That arrow, smooth forward, never sharp backward, is a quiet cousin of the second law of thermodynamics. So heat blur, diffusion, and curvature flow are all the same geometric idea. Move toward the average. Erase the sharpest detail first.
Smoothing as a force of nature, patient, one-way, and universal.
Wherever something settles, softens, or spreads, the heat flow is quietly at work. To go further, Fourier's original heat work, Evans for the rigorous PDE, Grayson's theorem that every loop becomes a circle, and Crank on diffusion.
One simple flow, smoothing the whole world toward its average.
That's the geometry of heat. If it finally clicked, subscribe. It really helps. And I'll see you in the next one.